Okay, I wanted to show you a little demonstration of a couple of curve fitting scripts that I'm giving you for use in Lab 5 and Lab 6 to help you fit the simplified EKV model to what I would call a gate characteristic for NMOS and PMOS transistors. So what I have in my workspace is basically a measured set of data that I took from an ALD 1106. In fact, I think it's probably the data set that I showed in that sequence of 4 slides that I showed at the end of the EKV recorded lecture. But if I do semi-log y vg isat, maybe we'll show it as dots, you can see that I've got data here that goes from, probably like a nanoamp or so up to probably about 4 milliamps, maybe 5 milliamps, something like that. And this is saturation current, and this is the gate voltage. You can see here I have fairly dense data in this area where I've got the exponential straight line on the log scale, and then that density of data points gets thinned out a little bit as we go into strong inversion, and that'll turn out to be fairly important to get this EKV fitting function working. But the goal is to try to fit that log squared 1 plus e to the x over 2 function to these data. And the way that this conceptually is going to work is the same way as we fit the exponential, or that I recommended fitting the exponential, and that is you basically do some sort of nonlinear transformation on the data. In the case of the exponential, it's just the log. And then you try to fit a straight line using linear regression to the log of the data, and you back out the parameters in your model from the slope and the intercept of the best fit line. Well, in the case of this EKV model, it turns out we can find an inverse nonlinearity for that log squared 1 plus e to the x over 2. It turns out to be the log of e to the square root of x minus 1. And it turns out that unlike the exponential, there is a parameter embedded inside of this inverse function that we need to find in order to get that inverse nonlinearity to turn our measured data into a straight line. And so you'll see kind of how that works as I go through. There's basically you'll find two functions in the zip archive on the course website. One is called LINEFIT, and this is actually a useful function by itself, but basically you pass this in an x and a y vector, and it does linear regression. But instead of doing linear regression to the whole set of x and y values, what it does is it tries to find some consecutive range of at least 10 data points that fit a straight line to within a certain r squared value that's at least 1 minus a third parameter that you pass through this called epsilon. So epsilon's a small number. A typical value would be in the range of 5 times 10 to the minus 4 to 5 times 10 to the minus 3. What it will do is it basically returns to you, assuming you can find such a run of data points that fit a straight line that well, it will return to you the index of the first and last points that it used, the number of points that it used, and then the slope and the intercept. And it's actually looking for the run of points, the longest run of points that fits to within this 1 minus epsilon r squared value that has the steepest slope. That seemed like the most useful criterion to latch onto. You have the script. You can actually see how it works, and you can change it to suit your needs. But that's the way it works out of the box. And the other script is called EKVFIT, and this is the help comment on that. And it basically sort of tries to explain to you what it's doing. And it's probably easiest for me to show you interactively with this data set kind of what it's doing. It does take an optional fourth argument here, besides the gate voltage, the saturation current values, and the epsilon parameter. It also accepts a fourth argument, which is a string, and if you pass it the string on, it turns interactive plotting on, so it will show you what it's doing at each step of the way. I find that useful for explaining what's going on in the script, and also for debugging purposes. So if you get some weird error message or it returns imaginary values for the parameters, it's best to probably turn that plotting on and see kind of what it thinks it's doing. So the return values are basically the three parameters: the specific current IS, the threshold voltage VT, and the value of the subthreshold slope factor, which is kappa. And so paste that and say EKVFIT, VG, ISAT, and I'm going to use, let's say, 5 times 10 to the minus 4 for this, and I'm going to turn the plotting on. And so you can see here, it's now attempting to fit a straight line to the log of the data using LINEFIT, and it is showing you in, let's see if I can get this a little bit bigger here. It's showing you in red the region of points that it's actually using for this fit. It's showing you the fit, and that looks like a very reasonable choice for the weak inversion region. And it's basically waiting for you to hit a key. So it's using a pause statement to wait until you hit a key before it proceeds. So if I hit a key, it goes and it basically tries to fit a straight line to the square root of the data to find the strong inversion region. And this is the range of points shown in red that it's chosen for that straight line fit. And that looks quite reasonable for a starting point as well. And so what it does is it basically takes the weak inversion range of points and takes a strong inversion range of points, and it takes the union of those two things plus the intervening points, which must be moderate inversion, and tries to find a good value for IS. And what it does is it basically says, okay, if I extrapolate this straight line back here, here's a guess for the threshold voltage, about 0.57, and it looks at the current and it tries to find the current at threshold. Says, well, IS is like twice the saturation current at threshold. That is used as a starting point for an optimization that basically tries to optimize the straightness of the line that we get when we apply the inverse EKV function with that value of IS to the data. And it's basically now going to try to find a value of IS that minimizes the curvature of this line. And so the next several sort of plots here are just showing you that iteration process, and you can see that it's started out at like 700 nanoamps for IS, and now it's settled more on something that's around 1.64 microamps, and the line is pretty decently straight. And so once it gets down to a certain stopping point, it says, okay, let me fit a straight line to get slope and intercept, and this is the EKV fit that it has arrived at. And so these are the three parameters up here. IS is about 1.64 microamps, VT is about 0.576 volts, and kappa, which is the slope of the exponential here, assuming a value of UT of about 25.6 millivolts, which is sort of the 300 Kelvin value to like 3 significant digits. And you can see it's done a pretty nice job. It doesn't get what's going on up here because that obviously was excluded from the fitting range, and actually if you were to try to enforce that to be part of the range, it wouldn't get a very good fit in this region down here. So it shows you that on a semi-log scale, and it shows you on the square root scale, and then it's done. So at this point, if we go back out to the workspace, we get the return values, and and that's that. So I will say a couple of things about this. One is that if your data is too dense up in the strong inversion region, it will likely latch on to some part high up in strong inversion as the weak inversion region. And that's because the values are bigger up there, and the nonlinearity is soft enough in the polynomial sort of quadratic region where it will be a better straight line fit to the weak inversion region. And so you may get some warning that says, or error message that says, the weak inversion current levels are higher than the strong inversion ones, or something like that, and it'll just exit. And so you should try to ensure that your data is dense in the weak inversion region and less dense in the strong inversion region. And you may have to either do the simulation sweeps in two pieces and then splice them together so that you can achieve that kind of data density, or you could do it all with a uniform spacing and then subsample by slicing in Matlab or something like that. If you have trouble with your fits, you can send me your data and I can help. I can give you some suggestions. I'm happy to do that. But and of course you're free to try to do the fits in other ways yourself. That's fine. You can probably you're not going to find something in the curve fitting toolbox that is the EKV model. I guarantee that. But you probably can in the curve fitting toolbox define your own sort of user defined nonlinear function, I imagine. And usually those nonlinear least squares curve fitters require you to do something like the partial derivative of the nonlinear function that you're trying to fit with respect to each of the parameters in your model. And they usually require you to provide some kind of starting values for those parameters, and it'll do something like a gradient descent to try to minimize the least squared error. And so if you'd like to try your hand at doing something like that with MATLAB's curve fitting toolbox or some other nonlinear least squares curve fitting toolkit someplace, you're more than welcome to do that. The functions that I've provided you are something that I work with myself and have found useful, but your mileage may vary, and you're free to do what you would like with that. But they're just there for you to use if you would like to try. So I think the other thing I'll mention is that the function is set up to assume that you are looking at a NMOS transistor. Obviously, you're going to have to be using it to fit the characteristic of a PMOS transistor as well. And you can basically transform your PMOS characteristic into an NMOS-like characteristic by, instead of passing it VG, you can pass it VDD minus VG. And so if VDD is 5, you just pass it in 5 minus VG, let's say, for instance, and that will flip it around so that it looks like it is an NMOS characteristic, and the parameters you get out should be fine. So anyway, that's EKVFIT. Okay.